In this lesson, we're going to be looking at solving our linear inequalities, and we'll use a lot of the same processes that we did in solving our linear equations. One of the differences in this section is we're going to use what we call a set builder notation, which may be a little bit different from the notation that you're used to using, and we'll also use an interval notation. And so I want to start out by going through these different uh, notations, and I'll include how you've probably done it in the past, and then also how these are going to look. So we have what we call an open interval. Now, in our set builder, let me just call that SB, set builder. The way that we would write our answer is it's the set, using those set braces, of all x's such that, this straight line down means such that A is between x and b. Now what we mean by an open interval, is this does not include the a and b. It doesn't include the endpoints. Now if we write this in what we call interval notation, then the way we would write this would be a parenthesis a, comma, b. Now you might notice that looks a little bit like an ordered pair. So here is where you have to deal with the context. What are you talking about? Are we talking about a point on the coordinate plane that has both an x and a y? Or are we talking about an interval that your number is going between? And then we have what we can graph this. We're even going to graph it a little bit differently than you may have in the past. So if we have our number line, and we have our points A and our point B. Normally, what you would do in the past is you would put circles there and you would leave them open to show that it doesn't include that circle. But on our graphs now, instead of putting the circles, what we're going to put is it's going to look like a parenthesis there to show that does not include those points, but what we're talking about are the points that are in between. So all of these would be the same solution set for a linear inequality. Now we can have what's called a closed interval, which means that we're going to include the endpoints. So the way we would do that in our set builder notation, we would have our set, it's all x's, such that a is less than or equal to x and x is less than or equal to b. It includes those endpoints. In our interval notation, to show that, what we put instead of the parenthesis there, we're going to put a square brace, and that shows that those endpoints are included. On our graph, we'll have our points A and B, and what we will do is we will put a square brace. What you used to put was a circle that you filled in, but here we have the square brace, and then we're talking about what all's between them. If we want to talk about where it starts and goes to infinity, so one type of infinite, let's say it's going to positive infinity, then we would say that we're talking about all the x's such that x is greater than, or it could also be equal to that value, depending on what you want. Now, the way that we show this, it's going to be those points that's greater than A. So A is going to be the smallest amount. Since I didn't say that we included the A, we'll use a parenthesis. If we had included it, we would have used a square brace, comma, and then it goes to infinity. Now, it can never include infinity because there's not a biggest number. On our number line, what we would have is A, and in this case, it's not including it, and we would have our parenthesis and then going toward infinity. Okay, another one that deals with infinity, let's say it was going toward negative infinity. It was a value and then all the values that were smaller than that. Well, in our set builder notation, it's the set of all x's such that x is less than that number. So in this case, our smallest value is negative infinity. So in our interval notation, we would start with negative infinity. We end at A, and either that point is included or not included. If it's included, you do a square brace. And then on our graph, my lines are not too straight there. We're starting from infinity and we're going to A, and we have our open parenthesis to show that it's not including that point. If it had been including that point, then we would have put uh, a square brace. So what we have is our open parentheses those show that the endpoints are not included. Our square braces show that the endpoints are included. Now you can have what we call half open. In set builder notation, an example would be it's the value of all x's such that it's going to include one of the endpoints, but not both of them. So maybe A is less than or equal to X, and X is less than B. So in our interval notation, it's including the A, so we use the square brace, but it's not including the B, so we would use a parenthesis. If we graphed it, then at A, we would have our square brace, and at B, we would have our parenthesis. Notice these turn into where they include the line. We're talking about what's between them. Another example of a half open, all x's such that maybe it doesn't include the A, but it does include the B. Then it would just be the other way around. We would have be the other way around. So we would have the parenthesis A comma B, and we would use the square brace at the other end. And so on our graph, we would have our parenthesis for A, but we would have our square brace for B. Now it's possible that we have all reals. So if we were talking about the set of all reals, then we would be talking about the set of all x's such that x is a real number. We're talking about everything on our number line, so in interval notation, it would go from negative infinity to positive infinity. Now it can never include infinity, and then our graph would simply be the whole number line, and it would include all of those values. So if we wanted to write some specific ones. Let's say that we wanted to write the interval. Our solution set was all the values between -2 and 5. We're including -2, but we're not including 5. So in set builder notation, this is the set of all x's such that x is between -2 and 5, and it can equal 2, but it doesn't equal 5. This would be an example of a half open. When we graph this, then we have our square brace at -2, but we have an open parenthesis at 5. And we're talking about all the values between them. If we had from 1 to 3.5, and it included both of them, so we would call that inclusive, then it's a set of all x's such that 1 is less than or equal to x, and x is less than or equal to 3.5. And you need to be able to write these no matter which one you're given. If you're given the set builder notation, then be able to write that in interval notation. If you're given the graph, then be able to write in either one of the other forms. So on our graph for this one, we start at 1, it's included, we go to 3.5, and it's included. And we have those values in between. If we went from -infinity to 1, we'll just make this an open one. Then it's a set of all values of x such that. Now, we're wanting from -infinity to 1, so we're wanting all the values less than 1. As we graph this, we're starting at -infinity, and we end at 1. And so this is how our graph would look. Okay, we're going to take some of these sets and we're going to do some intersection and union. When we talk about intersection, this is our symbol for intersection. Okay, what we're talking about is what the two portions have in common. If you think of a street intersection, that's the part of the street that's actually both streets. You could have Main Street here, and you could have First Street here. Well, everything that's on this street is on First Street. Everything that's on this street is on Main Street. But this portion right here in the middle, which we call the intersection, is on both streets. That's the part that they have in common. So that's our intersection. Now our union, which looks kind of like a U, makes it a little bit easier to remember. The union of two sets is the total amount for either. So that would be everything on Main Street and everything on First Street. So that would be putting it all together, is having what we call the union. And so these are our symbols that we use for union and intersection. So we're going to talk about taking some intervals and doing the union and the intersection of them. If we have, and we're going to write these in interval notation, 1, 4, and we want the union of that with the interval, and it's a closed interval of 2 comma 8. Now, one way that we can do this, and it makes it a little bit easier to see, is we could just graph each one. If we graphed 1 comma 4, then we would have 1, 4. And we're wanting everything that's in between those. Now, if we graphed 2, 8, and I'm going to rewrite this graph. So right here we've got 2, and then 8 would be on out here. Okay, what we're wanting is the union of these. So we're wanting everything that's in the interval 1, 4 combined with everything that's in the interval 2, 8. And so what we end up with is everything from 1 all the way up to 8, and it will include 8. So our solution set would be uh, 1 and then 8. Now it doesn't include 1 because neither one of them included 1, but it does include 8 because the second one included 8. So that would be our union. Now if we had the set 1, 3, and it's a closed interval, and we want to intersect that with 2, 6. And we're having an open interval. Okay, if we graph the 1, 3, here's our 1 and our 3. Then we want 2, 6. So 2 would be here, and we'll put 6 out here. Now what we want is what was common to both of them. Well, this part was common to this one, but not to this one. So we can't include that. What we have to do is look, this is where it starts, but now since the 2 was not common to this one, we can't include the 2, but we'll still have that open interval there. And then it's everything up to what was included in both of them, which was the 3. There's stuff out here that was common to this one, but it wasn't common to this one. Now 3 was in both of them because it was a closed interval for that. So we're looking at 2 comma 3. It includes the 3, but not the 2. And if we had that same 1, 1 comma 3, union 2 comma 6, oops, and it's an open interval, and we wanted this one. Well, as we look at our graphs for these, we start out with 1, 3, and then we want to do 2, 6, now we want to put it together. We want everything that was in this one combined with everything that was in this one. So what we're wanting is all the way from here to here. Now, we would write that the 1 was included in this one, so we would have it, would be a square brace, and we go all the way to 6. But 6 was not included in either one of them. And so that would be our answer for that one. Next, we want to look at solving our linear inequalities. and we'll solve them same way that we solved our linear equations, except for a couple of things. And that deals with our multiplication and our division by negative numbers. Now, we can add the same thing to both sides of the equation. We can subtract the same thing from both sides. We can multiply both sides of the equation and divide both sides, but some things are going to happen when we multiply or divide. So what we deal with is when you multiply or divide both sides of an inequality, by a negative number, then you have to reverse the sign of inequality. As an example, if we have the equation negative 3x is less than 6. Well, if we divide both sides of our inequality by negative 3, then we're going to have to reverse our inequality. We'll switch the signs because our answers have to be greater than negative 2, or in interval notation, negative 2 to positive infinity. Any of those answers would make it true. If you pick just one of them, uh, 5 would be in that set. Well, negative 3 times 5 is negative 15. That's less than 6. But if you pick something that wasn't in the set, a number on this side, such as uh, negative 5. Well, negative 3 times negative 5 is positive 15. So that wouldn't make it true. So this is what ends up happening when you multiply or divide both sides by a negative number. As long as you're multiplying or dividing by a positive number, nothing will change. In addition and subtraction, nothing changes. So let's take our equation 3x minus 7 is greater than or equal to 13. We solve it just like a linear equation. We're going to add 7 to both sides. So we have 3x is greater than or equal to 20. Then we're going to divide both sides by 3. Now we're dividing by a positive number, so our inequality does not change. And we would have x is greater than or equal to 20/3. In interval notation, okay, 20/3 is our smallest amount, and it can include that. So we would start at 20/3 and we go to positive infinity. Sometimes it's a little bit easier if you graph it first. We start at 20/3 and we use the square brace and we're going to positive infinity. We're talking about all the numbers that are greater. So that would be how we would graph it. You don't need to worry about putting a lot of numbers on your number line, just the ones that are part of our solution. If we have 18x plus 45 is less than or equal to 12x minus 8. Okay, we're going to solve this. Most likely we would subtract 12x from both sides. well, 8. So we would have 6x plus 45 is less than or equal to negative 8. Then we would subtract 45 from both sides so that we have our variable term alone. So 6x is less than or equal to negative 53. Then divide both sides by 6. Now again, we're dividing by a positive number. So our inequality stays the same, less than or equal to negative 53 sixths. You don't need to change that to a decimal. You don't need to change it to a mixed number. So it doesn't matter that our answer was negative. It's what you divide both sides by. So if we graph that one first, we have our negative 53 sixths. We're talking about what's less than or equal to that. So we're talking about what's going in this direction. So if we write that then in our interval notation, we're starting at negative infinity and going to negative 53 sixths. It includes that endpoint, but it can never include infinity. Our next example, say that we've got 7 minus 4/5 x is less than 3/5. Okay, we have a couple of things we can do with this. We can work with the fractions, but just like back with our equations, if we had fractions, we usually multiplied through by the common denominator. It makes it a little bit easier. So in this case, our common denominator is 5. So we're going to multiply each term by 5. As long as we're multiplying by a positive number, we don't do any changes. So we end up with 35 minus our 5's cancel, and that gives us 4x is less than our 5's cancel, and we're left with 3. Now, let's subtract 35 from both sides. So we have negative 4x is less than negative 32. Dividing both sides by negative 4. Now, since we divided both sides by a negative number, we have to change that inequality, and that would give us positive 8. So if we graphed it, we have 8, and we're talking about what's greater than that, but it doesn't include the 8. So we're talking about everything that's to the right of 8. If we write that in interval notation, it's going to be 8 to positive infinity. And this way, in doing this, in this notation then, our interval notation looks like our graph and makes it a little bit easier to transfer it one to the other. We can have parentheses. 4 times 3x minus 2 minus 3x is less than 3 times 1 plus 3x minus 7. Wow. We still go through and remove our parentheses just like we would with an equation. So we're going to have 12x minus 8 minus 3x is less than 3 plus 9x minus 7. Combining our like terms, 12x minus 3x would be 9x minus 8 is less than 9x minus 4. 3 minus 7. Getting our variables on the same side, we'll subtract 9x from both sides. Well, it drops out here, we're left with negative 8. It drops out here also, and we're left with negative 4. and the sign between them was less than. So then we ask ourselves, is that a true statement? Is -8 less than -4? It is. So this means that all reals are our answer. This is what we would call an identity. All reals. Now the way we write all reals in interval notation is we go from -infinity to +infinity. That says it's every number. The way that we write it on a number line is you just do your graph, and it includes everything. Fill that in. So we can even have identities. Now, if it had been a false statement, then there would be no solution. Okay. We can write our identities as compound statements, which showed our intersection or our union. And so we can write them with compound statements, and we want to look at that. We can write our and, which is an intersection. We're talking about what's on this and on this. So it's what's common to both of them. That would be an intersection. We can write that instead of in two separate statements. Many times we can write it in one statement. We can say 7 is less than x plus 5 and x plus 5 is less than 11. And this is what we call a compound statement because it's talking about two different inequalities. Now, what you can do is you can think of it as two separate inequalities. If we took this part over here and covered it up, and we were left with 7 is less than x plus 5, then to solve that, we would subtract 5 from both parts. Well, if we covered up the 7, and we looked at the other, x plus 5 is less than 11, to solve that, we would subtract 5 from both parts. So what we do in a compound statement is we look at this and we decide, what do we have to do to solve for x? Well, we would subtract 5. And if we're going to subtract it from one part, we have to subtract it from all the parts. So we're going to subtract 5 from all of those. We're left with 2 is less than x, and x is less than 6. Or in interval notation, 2, 6. We could solve another compound inequality. 3 is less than or equal to 4x minus 3 is less than 19. Well, what we would do here to solve to get x by itself would be to add the 3. So we're going to add 3, but we're going to add it to all three parts. That gives us 6 is less than or equal to 4x, and 4x is less than 22. Now we want to solve for x. Well, it's 4 times x, so the inverse operation would be to divide by 4. So we're going to divide all three parts by 4. This reduces to 3 halves, and this reduces to 11 halves. So x is between 3 halves and 11 halves. In interval notation, we would use square braces because it also equals. If we graphed it, we would have our 3 halves, our 11 halves, and we're talking about what's between them. But it does include the endpoints. Let's look at one more. If we have -6 is less than or equal to 1/2 minus 4, and that's less than -3. Now we could go through and multiply everything by 2 and get rid of our fraction. I left off the x, 1/2 x. But since it's only our coefficient, we could also leave it. That's the only place, and it's the coefficient for our variable. So this time I'm going to leave it. But if you want to, you could go through and multiply everything by 2, have negative 12 is less than x minus 8 is less than negative 6. And you could solve it that way. But I'm going to start this out by adding 4 to both sides. A lot of times if my only fraction is the coefficient of my variable, then I just leave it and work with it. So we have negative 2 is less than or equal to 1/2 x, and that's less than 1. Now what we want is 1x. Well, we know if we multiply reciprocals, we get 1. So the reciprocal of 1/2 is 2, and here we're doing what we just talked about. We're multiplying everything then by the 2 because we want to get rid of our fraction. Now we multiplied everything by a positive number, so our inequalities do not change. So we end up with negative 4 is less than or equal to x, and x is less than 2. Interval notation, it includes the negative 4, so we would do a square brace, but it doesn't include the 2. In graphing, it's going to include the negative 4, but it's not going to include the 2. It's everything that's between there. All right, that it is solving our inequalities and our compound inequalities. The next thing that we will look at will be our absolute value inequalities, and we're going to do that on the next part 2 of this lesson.